Hi guys, welcome back from spring break. Today we're going to do unit 14. We're into fourth quarter now. We only have units 14, 15, 16, and 17. So 4 units left. They'll go pretty fast. I posted this unit 14 in Google Classroom. So if you have a printer, print it. If you don't have a printer, I would just try to take the main part of the notes. If you can't figure that out, I can help you figure it out. Or if that really doesn't work for you, just shoot me an email and I can print it and mail it to you. But next unit, I'm going to try to do something a little bit different. So it'll have less practice problems and the notes will be real short. Practice problems will all be online. Okay, anyhow, let's get busy. Okay, so take a minute here, guys, to fill in the top part. This is from unit 13. And then when you come back, we'll go over the answers. Okay, so what do each of the arrows represent? So arrow number 1 is where you're starting. So anything you start with in a reaction is called your reactants. This is potential energy of your reactants. Arrow 2, we don't necessarily talk about a ton. This is the activated complex. Arrow 3 is normally right here. So that might have caught you off guard. This is forward activation energy. So the energy to start a reaction. Okay, and then number 4 is probably the most important one. It's the difference between your products and your reactants, and that is your delta H. You could also call it heat of reaction, or you could call it enthalpy. They mean the same thing, all 3 of those. So this is basically just the heat gained or lost in a reaction, and since this heat is given off, it is an exothermic reaction, so the heat lost. Okay, what 2 arrows combined make up the reverse activation energy? Go from here to here, so it would be arrow 3 and arrow 4, and then draw what would happen as a result of adding a catalyst. The hill would go down. Okay, so let's move on to the next page. Okay. I'm not very good at just changing this stuff with the pen. Okay, so rate of reaction is basically how quickly a reaction occurs. So if you think of things that we all, like we measure rate of, like speed in your car, like miles per hour, you don't have to write this down. Or if you're like at the doctor's office and you're talking about your heart rate, beats per minute, it's always like a change in value over time. So the one that we talk about mostly is a change in concentration. I'll just put A, like of reactant A, over time. So you're just looking at like, how are your reactants changing over time, or how are your products changing over time? In order for a reaction to actually occur, particles must have an effective collision. So particles are constantly bumping into each other, but not all those bumping into each other or collisions actually cause a reaction to occur. They have to be what's called effective. So in order for them to be effective, particles must have the correct position. You could see the word orientation. So like in this picture here, when they bump into each other, they're not properly oriented, so they just bounce off. In this one, they are properly oriented, so you get a bond forming. They also need to have the correct energy. So they have to have enough energy for the reaction to occur. So they have to have the correct activation energy for the reaction to occur. Okay, so before we do page 2, I want you guys to watch this really cute TED Ed that I'm going to share because I think it's really good and important to watch. Okay, so let me try to get to that. Okay, so let me try to share my screen. And if you can't, you might not be able to hear it super well, and I will try to post that. Oh, what am I doing? Okay. Cancel. Stop share. Let me pause this. Okay, we're back. Sorry about that. Okay. Let's go here and let's watch this video.
Elena, someone burned down your house with you inside. Do you know anyone that would do? Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on a few missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date for the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions will take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? And a matchmaker will help with this. A matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet in the correct configuration and allow a reaction to take place. So to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants a chemical reaction to occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated through the 5 methods I've described.
Okay, so I really like that video. I think it does a good job and it's pretty cute. Okay, so let's continue on page 2. Okay, so looking at the first one on page 2, it says blank. As kinetic energy increases, the number of effective collisions increase. So remember that kinetic energy, average kinetic energy is the same as saying temperature. So the first one that, first factor that affects rate is temperature. So this is a picture of lower temperature. This is a picture of higher temperature. So when there's more kinetic energy, the effective collisions increase and it makes the reaction go faster. Okay, on the next one, we are going to talk about concentrations, like increasing the number of people in the hallways. Okay, or in the school. So low concentration, you have a few collisions. Higher concentration, you have more collisions. So the more collisions you have, that means there's a greater chance that some will be affected. So it makes the reaction go faster. Okay, number 3 is surface area. So in the little video, it was about the group traveling in like a cluster. So this is a picture, I think it's helpful to see what surface area is. So in this picture, your surface area is the area that's exposed. So you have those 4 surfaces exposed. If you break it up, you break up your group, you have lots of area exposed. You have 4 sides on each cube. So it ends up being a lot more surface area exposed. So like all these inside pieces would be exposed as well. So the number of particles exposed increases your effective collision and it makes your reaction go faster. Remember that surface area is something that would only apply to solids. Like you can't make the surface area of a gas greater. Okay. Alrighty, so let's see, in this next one. So adding a catalyst is the 4th factor that increases the rate of reaction. So it does this by lowering both the forward and reverse activation energies. So this is the forward activation. This is the reverse. Remember, when a catalyst comes in, the hill gets lowered. So it would just lower both of those arrow. So less energy would be needed to start the reaction. Additionally, the Regents likes to talk about the alternate pathway. So it provides an alternative pathway for the reaction to occur. Catalysts are not involved in the overall reaction, and they don't change the energy of the starting and ending point. Okay, so those four are like the things you're going to use as your answers to questions that are going to come up like on the next page. One more thing also affects how fast things go, and that's the nature of reactants. So that really just depends on like what is being added together. Certain things react faster than the others, and it kind of depends. One thing it depends on is their polarity. So compounds with similar polarity, so that's like water and vinegar, they have the same polarity. They're going to have reactions occurring everywhere. So they're going to have more reactions. Something with different polarities like water and oil, water. Get down, you don't need any more candy. Is just going to have the collisions are only going to be occurring right here at the line. So whereas this one they're occurring all over, this one they're occurring right at the line. So back into your notes, compounds with similar polarities will have more collisions, and therefore they will have a higher rate of reaction. Okay. That's your last one. Okay, flip to page 3, and I'd like you to pause the video and take a few minutes to answer questions 1, 2, 3, and 4, and then that's it. Okay. So by the time I'm probably figure out how to change this page, you'll be ready to flip. Like seriously, why am I so bad at this? Oh, there we go. Okay, so maybe you watched me struggle through that, and I'm sorry you didn't see that. Okay, so 2 things necessary for an effective collision are on page 1. They need the correct position, and they need the correct energy. Okay, 2 ways to speed up this reaction. So this reaction, we have a bunch of gases. So remember, there's 5 factors. There's 4 really that you're going to use. Temperature is 1. Concentration is another. Surface area you're not going to use because these are all gases and you can't break up gases. You could have said a catalyst also. Okay, number 3, based on collision theory, why do we keep milk in the refrigerator? So in the refrigerator, temp is low, obviously, which decreases collisions. So since there are less collisions, the rate that milk spoils would also decrease. Okay, and then number 4, 2 students are having coffee in the commons. Student A adds 2 cubes of sugar. Student B adds 1 spoonful of granulated sugar. Why does B get to drink her coffee first? Granulated sugar has a greater surface area. More surface area. And since it has more surface area, more collisions, it will dissolve faster. So faster rate. Okay, so that's it for day 1 of Unit 14. Alrighty, I'll talk to you later. Bye-bye.